Now we're going to look at adding 310 kilojoules to 100 grams of ice at minus 10 degrees Celsius. We're adding a lot of energy, and we already calculated that it took 2.06 kilojoules to bring it up to the melting point. It took 33.42 kilojoules to melt it. And now we need to figure out, are we in this region here? That is, when I add this plus this plus this, is it less than 310? Do I have enough energy to boil it? Or am I in the superheated steam region? So the first thing we do is we ask ourselves how much energy is required to bring this up to the boiling point. So I have Q3 is equal to MC delta T, where this is the C of the liquid water, which is 100 grams times 4.184 joules per gram degrees C. Now my final temperature is 100 minus the initial temperature, which is 0, because we started at the freezing point. This brought us up to the freezing point, but it converted it all to liquid. And when I do this in the calculator, I get 41.84 kilojoules. So this is 41.84 kilojoules. And actually I want to write that in red just because I'm writing these in red. 41.84 kilojoules. So how much energy did I spend to get to here? Okay, well, I spent 2.06 kilojoules to bring the ice up to the freezing point. I then spent 33.42 kilojoules to melt the ice. I then spent 41.84 kilojoules to bring it to the boiling point. So this comes up to 77.32 kilojoules. I added 310. I obviously have enough energy to start boiling it. Now we ask ourselves, do I have enough energy to boil it all? So I go back to the single phase phase transition here, and I have Q4, the energy associated with boiling it, and I'm going to ask myself how much energy does it require to boil the 100 grams and see if when I add that to these other energies, if it's less than or greater than 310. So Q4 is equal to N delta H vaporization. On the molar enthalpy of vaporization, I have 100 grams of H2O. It's really 100.0, but we'll leave that out. And it was 18.015 grams per mole of H2O. And the enthalpy of vaporization is 40.6 kilojoules per mole. I get out my calculator, and this is equal to 225.37 kilojoules. Okay? So it takes 225.37 kilojoules. Now, if I add the 2.06, the amount to bring it to the freezing point, the 33.42, the amount to melt it, the 41.84, the amount to bring it to the boiling point, and the 225.37, the amount to boil it all, I get 302.69, we'll call it 302.7 kilojoules. So all of this energy combined is 302.7. I added 310.0 kilojoules, so I have 7.3 kilojoules left over. So my Q5 is 7.3 kilojoules. That is, after I brought it from the minus 10 up to 100 and boiled all the water, I still had 7.3 kilojoules left over. And I can ask, what is the final temperature when I add these remaining 7.3 kilojoules of energy to my steam at 100 degrees Celsius? So I have a superheated steam. Q5 is equal to M. Now I'm going to use C sub V, because I was using C sub S for solid, C sub V for the vapor, delta T, which is equal to m C sub V Tf minus Ti. I'm solving for the final temperature. The final temperature is equal to the initial temperature plus Q over m C sub V, which is equal to, now I'm at 100 degrees. I've brought it up to 100 degrees. And I have 7.3 kilojoules of my original 310 remaining. I'm adding this to 100 grams. Since this is in kilojoules, I'll write the 100 grams is 0.1 kilograms left over of the mass. That's how much water I have. And the specific heat capacity of the vapor is 2.01. Now I'm going to convert these to kilojoules over kilograms, degrees C. Okay, now this becomes 100, and it was really 100, and I now add to this this number here, which has 2 sig figs, so this is 36, and this will give me a final temperature of 136 degrees C.